What I want to do in this video is think about how my blue hydroxide ion right here might react with the various molecules that I have drawn in yellow. And what I want to focus on first is how these yellow molecules are different. So right over here, I have a carbon bonded to 3 hydrogens and a bromine atom. And so this right over here is bromomethane. But the important thing to think about in consideration of what we're going to talk about in this video is the fact that the carbon, other than the fact that it's bonded to the bromo group, it only is bonded to other hydrogens. So we could call this a methyl carbon. Methyl carbon. What about the carbon in this case, right? This is bromoethane. Well, over here, this carbon, it's definitely bonded to the bromo group, but it's also bonded to another carbon. It's bonded to this carbon right over here. So in this case, we would call this a primary carbon. It is bonded to one other carbon. Well, what about this one over here? Well, you see immediately it is bonded to 2 carbons, this carbon and this carbon right over here, so we would call this a secondary carbon. And this carbon right over here is bonded to 3 other carbons, 1, 2, 3. So we call this a tertiary carbon. And as we'll see through the course of this video, the type of carbon we're dealing with, how many other carbons we're bonded with, will dictate what type of a reaction might occur and how fast that reaction might occur. So let's go to this situation right over here. This hydroxide ion is a reasonable nucleophile. So let me write this down. This is our nucleophile. It's going to be the nucleophile in every scenario that we're talking about. And when we talk, just as a review, nucleophile is something that is seeking a nucleus, or I guess another way you could think about it, it's looking to give away its electron. And similarly, you can imagine this right over here, this bromine, it could be a pretty good leaving group. It doesn't mind accepting an electron. So, and I'm not going to talk too much about the solvent. We'll just assume that the solvent is appropriate for this type of reaction. You could imagine that the nucleophile right over here, this hydroxide ion, might want to give one of its electrons to this methyl carbon. And right as that is happening, the bromine can take back an electron, or take an electron, I should say, and become a bromide ion. Now, we've seen this type of reaction before. We call this Sn2. We would call this, let me do this in purple. We would call this an Sn2 reaction. Why is it Sn2? It's substitution. We're substituting the bromine with the hydroxide. Why is it N? Well, N for nucleophile. And why is it 2? Well, 2 is because in one step we have both of the reactants are reacting. Or another way to think about it, the rate determining step involves both of the reactants. And in SN1, you have one thing leave and then the other thing comes back. It happens in different steps. Here, the rate determining step, both of the reactants are reacting. Fair enough. And for the sake of this video, because we want to compare what reaction happens and how fast it happens, here we'll say that this is happening quite fast. Quite fast. And we'll see the difference here is how easy it is for the nucleophile to access the carbon that it is reacting with. Here, it's very easy for it to access it. There's nothing getting in its way. Now let's look at this scenario right over here. Well, once again, we can imagine our nucleophile wanting to give away one of its electrons to the carbon, and then the leaving group taking an electron away and becoming a bromide ion. So once again, we are going to have an Sn2 reaction. But in this case, it's going to happen a little bit slower than what we saw in the case right here over the left. Why is that? Well, this other CH3, this is much larger than just a hydrogen would be. And so it's kind of blocking the nucleophile from approaching from certain directions. Remember, all of what we do in organic chemistry and chemistry, it seems like these neat and clean reactions where everything knows what to do, but these aren't intelligent creatures. They're just randomly bumping into each other. And if you have this big CH3 sitting here, that's going to block the nucleophile from approaching from that direction. In this case, right over here, hydrogen is a very small atom. It's not going to really block as much as this entire CH3 is going to. And because of that, we're going to still have the Sn2 reaction, but it's going to occur a little bit slower. So maybe we'll call this quite fast, and then we'll call this a bit slower, a bit slower, a bit slower, but still reasonably, but still fast, but still fast. And obviously, I'm not giving you exact numbers, but we're talking about relative rates of reaction. Now let's go over here where we have a secondary carbon. Well, same principle applies. We can still have the Sn2 reaction. Our nucleophile gives an electron. Our leaving group takes an electron. So we're still going to have an Sn2 reaction, but now we're being blocked by more things. We have a CH3 up here, and we have a CH3 down here. So this reaction is going to occur. This reaction is going to be slow. Now finally, let's look at this situation. In this situation, we are really blocking the nucleophile from being able to get to the carbon. You have a CH3 over here, a CH3 over here, a CH3 is over here. Each of these are going to be much bigger than the hydrogens in this case. So in this situation, it's blocking it so much. It's blocking, I guess you could view the nucleophile's attack on that carbon. It's blocking it from so many different directions that you actually will not have an Sn2 reaction right over here. So let me write no Sn2 right over here. And this whole phenomenon, what we're trying to talk about in this video, where the reaction is determined by essentially how the shape of the molecule is and what might be getting in its way, we call this phenomenon, we call it steric hindrance. Steric hindrance. And what does it mean to hinder something? It means to kind of get in the way or make it seem like or make it harder for it to happen. And so in this case, the CH3 groups are large. They're hindering the nucleophile from attacking the carbon. And steric just means kind of the three-dimensional shape of it. The three-dimensional shape of it is keeping it from, or the three-dimensional shape is what is doing the hindering. And that's what we see in all of these cases. Now, the last thing you might be thinking about is, well, why can't it attack from this direction? Why can't the nucleophile go from that direction? And that actually is possible in an Sn1 reaction. In an Sn1 reaction, the leaving group leaves, and so there's kind of an opening for the nucleophile to come in later. But in this case, you actually have your leaving group that's in the way. It's going to block your nucleophile from attacking from that direction. So when we talk about Sn2 reaction, the nucleophile is coming from the nucleophile is coming from the opposite side from which the leaving group is actually leaving.